Hello, it's Mrs. Pound here, and I'm back with more about inertia from Chapter 4, Newton's First Law of Motion. And let's keep going. Now, last time we talked about inertia, and we talked about the history of motion, and we ended with inertia, which stated that an object in motion will remain in motion, and an object at rest will stay at rest unless it's acted upon by an outside force. So let's continue talking about that idea. Now, our objectives today are going to be to distinguish among mass, volume, and weight because sometimes these terms are confused, and to distinguish between the kilogram and the Newton as units of measurement. So in section 4.5 of your book, it talks about mass, a measure of inertia. So the first term I want to talk about is volume. This is the amount of space occupied by an object. Units for volume that you will commonly see used are milliliters, liters, cubic centimeters, and cubic meters in the metric system. Mass is the quantity of matter in an object. It has to do with how many atoms make up the object. It is also a measure of inertia or laziness that an object exhibits in response to an effort made to start it, stop it, or otherwise change its state of motion. Our measurement, our SI unit of mass is the kilogram. Okay, we also might use grams for smaller quantities, or even for smaller quantities, milligrams are common units that are used. Now, weight is different than mass. Weight is the force of gravity on an object. It is a force. And so weight is measured in newtons, and the SI unit of force is the newton, and it's equal to a kilogram times a meter per second squared. And we're going to see where that comes from. It comes from an equation here in a minute. And oftentimes what we use to measure forces, and therefore weight, is a spring scale, as you see pictured below. Now, to kind of distinguish between these terms here, let's talk about a few different things here. First of all, the amount of inertia an object has depends on its mass. More mass equals more inertia. So here, there is this big boulder. This boulder, in order to get it started, you would have to have a really big force because it has a lot of mass, so it requires a lot to get it going. But once it's going, it's hard to stop because of all that mass as well. Compared to, say, a feather, which has very little mass, so it's very easy to start it in motion, and because of that little mass, it's very easy to stop its motion. So inertia, the more mass, the more inertia. Now also here, let's consider this question. Which has more mass, a kilogram of cotton balls or a kilogram of nails? The answer is they have the same amount of mass. Because it's a kilogram, they have the same number of atoms in them. But here's a similar question. Which has more volume, a kilogram of cotton balls or a kilogram of nails? And the answer is a kilogram of cotton balls. They have less density, so they're going to take up more space. So, are volume and mass the same? No, they are not. They are different quantities. They measure different things. Here's another thing to ponder. Due to the lack of gravity in outer space, is it easier to shake a stone back and forth compared to on Earth? And the answer, surprisingly, is no. The amount of force needed to shake it is the same in either place. Okay? Because we're talking about back and forth, you're confusing it with weight. Weight is up and down. Weight is the force on it due to gravity, and in outer space, there's no force of gravity on it. But the back and forth, that's not affected by gravity, okay? The back and forth would be the same. It would be up and down that would feel different to you because of the lack of gravity in space. One important thing we need to know is that mass and weight are proportional to each other, but they are not equal to each other. And that is because weight is a measure of the force of gravity. And we have an equation that helps us to see that. And as far as weight and mass go, it's a matter of if you're in outer space, you have no weight if there's no gravity. You do have weight on Earth, but your mass is the same in either place. And if you're on the moon, your weight is 1/6 of what it is on Earth. But if we're comparing things on Earth, because gravity is affecting everything pretty equally on Earth, that's why it's proportional. So the equation that you can use to find the weight of an object, if you know its mass, is weight equals mass times acceleration, and that's the acceleration due to gravity. So W equals m times g, with g being 9.8 meters per second squared. We're not using 10 this time. So what is the weight in newtons of a 3-kilogram bag of apples? Using this equation, we always write the equation down first for any of these problems. We then plug in the numbers. So weight equals 3 kilograms for the mass times 9.8 meters per second squared for the acceleration. And when we multiply those numbers together, we get 29.4 newtons. And the newtons comes from the fact that a newton is a kilogram times a meters per second squared. We'll be doing more problems like these in class. So our objectives today were to distinguish among mass, volume, and weight, and to distinguish between the kilogram and the newton as units of measurement. Now don't forget your 5 questions, and I will be back and we'll be talking more about forces next time.